I have no intro today. Just welcome to math. There we go. All right. Square root of 144, guys. These are your 9.1 notes. So if you're at home, 9.1 is where we're at today. Pause the video now if you're not caught up with me. But square root of 144 is 12. We just talked about whether it's 12 or plus or minus 12. It's just 12. The square root of a number is positive. Now, if we are solving for a variable, like here, right? What uh, if we had x squared equals 144? If we were solving for a variable, we would take the square root of both sides, and then we would throw plus or minus in front of there. So x would equal plus or minus 12, but we were not solving for a variable here. On to the second problem. This is the square root of 9 over the square root of 25. This is equal to the square root of 9 over the square root of 25. So what's the square root of 9, everybody? 3, and the square root of 25 is? 5. So we get 3/5. Sometimes you can simplify that. We cannot. It's already simplified, I should say. So there you go. Next one. 1 second. Let's take a look at this one. Now, before we talk about this problem directly, let me give you an example that's similar to it. If I had 5x multiplied by, I don't know, 3x, 5 times 3 is 15. X times x is x squared. So we kind of treat this the same way. So 5 times 4 is 20. Square root of 3 times square root of 6 is square root of 18, right? 3 times 6 is 18. We're not quite done because 18 can be, square root of 18 can be simplified. There is a perfect square factor of 18. Who knows what it is? 9, right? So we can say this is 20 multiplied by the square root of 9. Now it's 9 times 2, right? 9 times 2. What's the square root of 9? 3. Now, what operation is happening there? Multiplication. So we're going to be multiplying outside as well. So that's 20 multiplied by 3. And then we're left with that 2. Nothing happened with it. It just stays under the radical square root of 2. 20 multiplied by 3, we get 60 square root of 2. So there is that example. Now let me talk about what I want to see. I definitely want to see this 20 square root of 18, okay? And then I'm okay with you jumping. If I were you, I would show one of these two. I don't need you to show both unless you just want to. I would show one of those two. If you're like me, when you have to hold a lot in your mind, and I'm not sure if that's a lot or not, but when you have to hold a lot in your mind, I tend to forget some stuff or like it just slips out, and I'm more likely to make a mistake. But I think if you show one of these two steps, you're probably not going to forget anything. So there you go. Let's take a look at this one now. 2 root 5 squared. Well, this is going to be 2 root 5 multiplied by itself. So go ahead and simplify that one. I think you can do that on your own. Okay. What's 2 times 2, everybody? 4. What's square root of 5 times square root of 5? 5. So 4 times 5, we get 20. Now, you may have written out square root of 25, which is equal to 5. I want you to realize this. Square root of 5 multiplied by itself is just 5. So anytime you have a square root multiplied by itself, the product is going to be just the radicand, which is the number underneath the radical. Or you might say something like this. What's the square root of 17 multiplied by the square root of 17? 17. What about the square root of y multiplied by the square root of y? Y. There you go. Because I asked that question, that's not there you go. Dumb. So dumb. All right. We get on that idea? That comes up a lot. So if you don't understand this, ask questions now. I think you already knew that, though. Okay. Take a look at that one. Think back to the one we did over here. These two are similar. So see what you can do on this problem. So if you think about the previous problem that was similar to this is going to be the square root of 4 over the square root of 3. And so you probably said 2 over root 3. And you're part of the way right, but you're not all the way right. The problem is the square root of 3 is an irrational number, right? That's an irrational number. And in mathematics, we don't like to divide by an irrational number. So who knows what we can do to make our denominator rational? Tommy?
Can you multiply by like square root of 3?
We can multiply by square root of 3 over square root of 3. Who can tell me what square root of 3 over square root of 3 is? It's 1. It's 1. So we multiply straight across, and square root of 3 times square root of 3 is 3. In the numerator, we just get 2 square root of 3. Now we have a rational denominator, and we're done. Sometimes at this step, you can simplify further. Like if this were like 2 over 4 or like 2 over 5, no, not 2 over 5, but like 2 over 6 might be a good example. You could simplify that. But this is already simplified, 2 over 3. Can't simplify that further. So we're done with that one. Questions there? Okay. On to the purple set. Square root of 75, square root of 108, and then square root of 6 times square root of 8. I think you can do all three of these. Give those a shot. I'm going to pause the video. You at home, try those out too. The first problem. We do have a perfect square factor of 75. You can rewrite 75 as 25 times 3. The square root of 25 is 5, so we get 5 root 3. I bet everybody got that one right. The second one, off the top of my head, I don't know any perfect square factors of 108, but this is a method that you can use, especially for larger numbers like this. It's called prime factorization. You make a factor tree. 2 times 54. 54 is 2 times 27. 27 is 3 times 9, and 9 is 3 times 3. So the prime factorization of 108 is 2 times 2 times 3 times 3 times 3, and you see all that right there. Now, here's a rule of thumb. Anytime you have two, like a pair of factors underneath the radical, you can take one out. So we can take 1, 2 out. We can take 1, 3 out. We have to multiply them, right? They're being multiplied under the radical. They need to be multiplied outside of the radical. And then we are left with the square root of 3 underneath the radical. And so our final answer is 6 root 3. Questions on that one? You may not have done that exactly the same way as I did. As long as you supported your work, I don't mind any method that you used. But I did want to show you that making a factor tree and writing out the prime factorization always works and is especially helpful with larger numbers. This next one here, square root of 6 times square root of 8 is in fact the square root of the square root of 48. I'm giving it away. Spoiler alert. What's the perfect square factor of 48? 16. Yeah, 16. So it's 16 times 3. If you want to show your work like this, I'm okay with that. I know what you're doing. So this is equal to, the square root of 16 is 4, and then we're left with the square root of 3. 4 root 3. So I wanted to show 3 different ways of showing supporting work, all of which are acceptable. I know what you're doing on all 3 of them. Questions on those?
Wait, so
yes.
On like a quasar dot, we have to show like the little tree thing.
No. Okay. So if you're at home, the question was, do we have to show the factor tree? I would just say if you're going to use the prime factorization, it's in your best interest to make a factor tree. I think if numbers are simple enough to do a factor tree mentally, it's probably also simple enough to not make a factor tree, kind of like this one up here, right? Yeah, I know this is 3 times 5 times 5, but why would I do that if I know that 25 is a perfect square factor? Try these 2 on your own. All right, the first one. Pierce, what do I have to do to rationalize my denominator?
You have to multiply both the numerator and denominator by root 6.
There you go. So square root of 6 in the denominator, square root of 6 in the numerator. When we do that, what do we get in the denominator, Pierce?
6.
6. And the numerator is just 24 root 6. Are we finished?
Yeah.
We're not.
No. And it's 4 root 6.
Yeah, 24 divided by 6 is 4 root 6. So you should have 4 root 6 there. Questions on that one? Okay. This one, okay, this is neat. Earlier, we had, let me find the example, like, for example, here. We said, okay, square root of 9 over 25 is the same thing as the square root of 9 over the square root of 25. It goes the other way as well. So let's go the other way this time and see what happens. So I'm going to write out this is equal to the square root of 80 over 5. What's 80 divided by 5? 16. What's the square root of 16? Isn't that nice? Questions on that one? Yes, Tommy.
Can we also do it like the original way where we just take the square, like simplify it, like another, like where you go and get like 2 square root, or yeah, 4 square root 5 over the square root 5, and then you can
Yeah,
multiply the square
yes
root
is the
5.
answer. Yeah. So like I know there's multiple ways to do this. So if you use an alternative way and you still get 4 and you support as your work, I'm totally fine with it. I just think this is probably the most efficient route, so it's good for me to show you that. Yeah. All right. Let's take a look at this one. So if we had the problem 3x plus 7x minus 6x, well, 3x plus 7x is 10x, minus 6x gives us 4x. Everybody's good on that, I think, right? It's the same idea here. So this is 3 root 2 plus 7 root 2. Well, earlier we had 3x's. We're adding to that 7x's. We have a total of 10x's. Here we have 3 root 2's. We're adding to that 7 root 2's. So now we have 10 root 2's. And we now have to subtract from that 6 root 2's. And we end up with 4 root 2's, or 4 square root of 2, you might say. Questions on that one? Okay. Let's take a look at the second one here. Y'all still need to write that. I kind of breezed up pretty quick. Okay. This next one here, square root of 20 plus square root of 45. It looks like these are not like terms. It looks like we can't add them. Please don't tell me this is square root of 65, because that's not true. This would be like we had x plus y. Well, we can't add x plus y. Not possible. They're not like terms. But, ooh, hang on a second. Gotta stop my video. It looks like they're not the same, but do we have any perfect square factors for 20? 4. So we get 4 times 5 is 20, right? So that's equal to 2 root 5. Good on that. And then 45, do we have any perfect square factors here? Yeah, that's 9 times 5. Square root of 9 is 3. So 3 root 5. 2 root 5 plus 3 root 5 is 5 root 5. Questions on that problem? Okay. Looking at this example, who knows what we should do here? FOIL, you're correct. We're going to FOIL here first. Let's do it together. 4 is first, 4 is first. 4 times 4 is 16. O stands for outside. 4 is on the outside. Negative root 3 is on the outside. A positive times a negative is a negative. 4 times root 3 is just 4 root 3. I stands for inside. Root 3 is on the inside. 4 is on the inside. A positive times a positive is a positive. Root 3 times 4 is 4 root 3. And then L stands for last. Square root of 3 multiplied by negative square root of 3. Well, a positive times a negative is a negative. Root 3 times root 3 is 3. So minus 3 there. Okay. Marshall, what can we combine here?
Well, you can combine the 16 and the 3.
All right, what's 16 minus 3?
13.
13. Anything else we can combine?
And the negative 4 root 3 plus 4 root 3 is equal to 0.
Yep, so we're just left with 13, right? 13 is our answer there. Questions? All right, let's go over to the red on the right. Oh. Oh, okay. Be careful on this one. You're going to want to say that this is 6 plus 8, which is 14. That's not what it is. Let's talk about why. Well, if we had the square root of 6 squared multiplied by 8 squared, notice we're multiplying here versus we're adding here. There are different rules that govern multiplication and addition underneath this radical. Just like in fractions, right? There's different rules for adding and subtracting with fractions as there are with multiplying and dividing with fractions. It's a completely different process. Seems like it'll be the same, but it's a completely different process. So up top in blue here, this is going to be 6 multiplied by 8, which is going to be 48. But that is not the case with addition. There are different rules that govern the addition. And so what we have to do is we have to actually carry out the operations. So what's 6 squared? 36. What is 8 squared? 64. What is 36 plus 64? 100. What is the square root of 100? 10. So we get 10 there. Now remember earlier I said you're going to want to say that this is 6 plus 8, which is 14. And notice it's not. It's 10, right? So please, please, please do not do this. That's never right. Questions on that? All right. Try the next two on your own. I think you can do this. So here we get the square root of negative 5 squared is what, Whit?
Oh, sorry. Square root of negative 5 is 25.
25. Plus, what about negative 12 squared?
144.
144. And so we get the square root of
169.
169. Now, maybe you know this, maybe you don't. The square root of 169 is going to show up a lot over the next couple weeks. It's 13, right? So if you don't know that, that's okay. It shows up so much, you're going to commit that to memory. You're not going to be able to help it. Square root of 169 is 13. So there's the answer to that problem. All right, on the next one here, we have 3 plus 5 root 2 squared. So it's 3 plus 5 root 2 multiplied by itself. And James, what do we have to do here?
So, I FOIL.
FOIL. What's 3 times 3?
9.
9. O stands for outside. What's 3 times 5 root 2?
15 root 2.
Yep, so plus 15 root 2. I stands for inside. 5 root 2 multiplied by 3 is
15 root 2.
15 root 2. And then last, okay, this is a little different here. James, what's 5 times 5?
25.
25. And then root 2 times root 2?
2.
2. What's going to happen between the 25 and the 2 here?
Multiplication.
Multiplication, right? The 5 root 2 and the 5 root 2 will be multiplied, and then we multiply both those together. These are going to be separated by multiplication. So now, let's combine like terms. 9 is just 9. 15 root 2 plus 15 root 2, what's that, Jamie? 30 root 2. And then, what's 25 times 2? 50. So 9 plus 50, we get 59. So 59 plus 30 square root of 2. Notice I wrote the non-radical term first. Please try to get in the habit of doing that. I'm not going to take points off if you don't write the non-radical term first, but it's just the way we write things in mathematics. So non-radical terms first. Questions on that? Okay. Now we have variables involved here. So x squared equals 16. X squared is equal to 16. John, what do I have to do to solve for x here?
Square root of
Yeah, square root here and square root here. Now we're taking the square root of a variable, so what has to go in front of this square root of 16?
plus or minus.
Plus or minus. So x is going to equal plus or minus what? 4. When we're solving for a variable, please don't forget that plus or minus. That is different from up above. We already talked about that at the beginning of class. So with that in mind, try the next one on your own. Wait, we take the square root of both sides. And what do I have to do in front of the 75 here, Elise?
Plus or minus 5.
Plus or minus, yeah. So x is going to equal, and you told me, what's the perfect square factor of 75?
25.
25. So it's plus or minus. What's the square root of 25? 5, and 5 root 3, right? What did I not show? I didn't show this step. This is plus or minus the square root of 25 times 3. You can show this. You don't have to. I'm thinking about this, even though I didn't show it. So square root of 25 is 5. We're left with square root of 3 under the radical. So there you go. There's your solution there. Questions on that one? Okay. Here, we are going to isolate x. How do we do that? Do that by subtracting 9 squared. So minus 9 squared, minus 9 squared. You don't just want to take the square root of both sides. You want to get x isolated. So when we do that, we are left with x squared equals, who knows what 15 squared is? 225 minus 9 squared is 81. So x squared equals, who knows what? Yeah, 144. 225 minus 81 is 144. So then, Georgia, what do we do to solve for x here? And I can wait if you're trying to catch up with the writing.
You square root.
Yep, square root of both sides. And what do we have to put in front of this 144?
Plus or minus.
Plus or minus. And so what does x have to equal there, Georgia? Yeah, plus or minus 12. Questions on that one? Okay. Try that next one out on your own. I think you all can do it on your own. Give it a shot. Use the one up above as guidance. 2 root 3 squared, what's that going to be?
That would be 4 times 3.
4 times 3, which is 12, plus x squared equals, what about 3 root 2 squared?
That would be 9 times 2.
9 times 2, which is 18. Bring down the plus x squared. So now what do we do to solve for x? Subtract 12 from both sides, minus 12, minus 12. We end up with x squared equals 6. Then what do we do? Square root of both sides. And so what's my answer? X equals? Good, plus or minus root 6. I should have actually had a plus or minus up there, but I was trying to trick Ricky, but it didn't work. It was too clever. Two are not new at all. You should be able to do really the next 3. So work the next 3 on your own. I'll be writing the answers up on the board. You can take a look up front. I could have given these to you at the beginning of class, and you should have known how to do them. So what we've just done over the last 40 minutes has nothing to do with these 3, but these are still solving quadratics. So give that a shot. They're not. All right, let's talk about the first 2 here. The first one here, you should get x minus 4 times x plus 1 equals 0. So x equals 4 and x equals negative 1. Just, hey, fair warning, when you get to future math classes, I think your teachers want to see this. X minus 4 equals 0, therefore x equals 4. And x plus 1 equals 0, therefore x equals negative 1. Now, my other classes, we've had questions about extraneous solutions. Remember, extraneous solutions only occur when the x value represents like an angle measure or a side length or something like that. We can't have negative angle measures, can't have side lengths. I get it, you Googled it, I know. Okay, so just keep that in mind. So there's nothing represented by this x value here, so no, neither of these are extraneous. Questions there? Hang on, about math?
Yeah.
Okay, yes.
So,
You don't have to show this. I'm not going to require this in red, but just know in the future they're going to require it.
okay, so the x has to represent something for it to be.
Extraneous, yeah. If it doesn't represent anything, if it's just like an abstract idea of like a number, then it can be negative all day long. Doesn't matter. Or positive. Doesn't matter. Here, we want to make sure we set this equal to 0, giving us x squared minus 8x plus 12. 2 numbers that have a product of positive 12, but a sum of negative 8. Well, if the product is positive, but the sum is negative, we know these are both negative, right? And those 2 numbers are negative 6 and negative 2. Negative 6 multiplied by negative 2 is positive 12. Negative 6 plus negative 2 is negative 8, giving us x equals 6 or x equals 2. Now, I'm going to factor by grouping in this last one here. We take A, which is 3. We take C, which is 2. We multiply them together. 3 times 2 is equal to 6. Then we take a look at B. B is the coefficient of the x term, which is 5. We want 2 numbers that have a product of 6, but a sum of 5. What are the 2 numbers? 3 and 2, right? 3x plus 2x. So 5x becomes 3x plus 2x. Everything else gets copied down. And it looks like this. And now it's called factor by grouping because we're looking at the front group first. What common factor do we have in 3x squared plus 3x? 3x is a common factor. So I'm going to write 3x out front. And then I'm left with what inside the parentheses?
X plus 1. X.
It's x here. And here's how you can check this. Use the what property?
Oil.
Distributive property. 3x times x, is that 3x squared? Yes. Plus, what has to go here? 1. Again, you can distribute in to check this. 3x plus 1, is that 3x? Yes, it is. Now we look at the back group. Here's a hint on how you start. You write down whatever's in parentheses again, x plus 1. We know that's going to be a common factor. And so now we look here, 2x plus 2. All right, well, what did we have to factor out of 2x plus 2 to end up with x plus 1? 2. Positive 2. We can distribute back in and check. 2 times x is 2x. 2 times 1 is 2. So there you go. So now we have common factors. We have common factors of x plus 1 in both of these. So I write down x plus 1. That was a common factor in both the front term and the back term. And we're left with 3x, right? 3x was here, plus 2. And I messed up on the step before. That should be equal to 0, and this should also be equal to 0. And so now we know that this is equal to -1. And then here, 3x plus 2 equals 0. X equals 3x equals -2. And so we divide both sides by 3, and we get x equals -2/3. So x equals -2/3, or x equals -1. Questions on that? John?
I just factored it from the original problem.
Did you just guess and check? It's okay if you did. That's a perfectly acceptable way to do it, right? If you're like, okay, I know it's going to be 3x, and I know it's going to be x, and then you figure out everything else. That is okay. In fact, I think the upper level math teachers actually kind of prefer that method. It shows a good number sense. So that's perfectly acceptable if you did it that way. Anything else? Is that what you're going to ask, Ricky? Okay. All right, good. All right, thanks for watching. Hope you have a great day. Hit that like button. Bye.